Maybe I'll.
Did you guys enough of you hear that?
We heard you.
Maybe I'll add a quick comment to that, which is the way that partial FTQC actually enables, reduced cube print is that is actually using trotterization, because you get lots of small angles, and that's what you pay the T cost for. Instead, that's what you synthesize with kind of post-selection, code growth, and so on. So that's precisely the trade-off one is looking for. And so I do think that, and what we found in one of our papers is basically there is a bit of a Goldilocks regime, namely there is an optimal number of T gates, which is roughly in the million, where doing partial FTQC has fewer qubit requirements and runtime requirements. Because if you start to go way beyond that, then the post-selection rate explodes. And so you don't want to go there. But 10 to the 6 is also roughly where Fermi-Hubbard simulation sits, 2D Fermi-Hubbard model. So it's kind of the sweet spot of applications for partial FTQC.
To follow up on that, I guess, so that's, sorry, we're kind of dodging the same piece. So that's the approach, that's the application. What are the considerations for the architecture that we need to start thinking about?
I'm kind of just spitballing here. So I haven't thought about how to do partial FTQC in this tightly integrated sense yet, but.
Well, sorry to cut you off, but we don't have to think about tightly integrated, right? Like, in terms of the workflow,
in terms
what
of
are the issues, and when is it that we have to start asking questions about the integration?
Well, you've touched on something, I mean, just to respond from an Alice and Bob standpoint, I think you've touched on something interesting that has implications more broadly on what we're doing. Alice and Bob's machine is extremely efficient as an architecture, as a concept, for fault tolerant. It's not something you would actually want to run a variational algorithm on its physical gate set. So what you're introducing is we now have a model for applications and algorithms that might actually be multimodality. And the question is not just the coupling between a classical HPC facility and some quantum unit, but in fact cooperation and coordination between the NISC and fault tolerant components of the application pipeline.
I have one comment and one question. The comment is about the data volume. So if the speed of the uploading the classical data to quantum computer is significantly slower than the network communication on the classical computer, then the volume won't be an issue, but the uploading to the quantum computer is actually the issue. A question is, I heard mentioning the partial fault tolerance. I wonder how do you define the partial fault tolerance? Which part is the non-fault tolerant part of the calculation?
It's the magic state distillation, and basically what you do is it's basically all the rotation gates. You do them in a non-fault tolerant way, and you do all the Clifford gates in a fault tolerant way.
Okay, thank you.
And then you can do kind of state cultivation, code growth, similar ideas from full fault tolerance, and you can use them to bound your post-selection rate. That's the main trick. That the post-selection rate should not explode as you're trying to synthesize these states.
I think a theme that will come up again and again is length scales in the quantum computing, where we may have fault tolerant zone that we focus on locally. Thomas talked about the embedding idea, and I think that's going to show up again and again because it gives you scaling. Kenny Mertz at the Cleveland Clinic just did a calculation on a protein this way with 12,000 atoms. So I think that theme of locality, I mean, you have to understand the length scale of the entanglement, I think. You can't beat that, but beyond that length scale, you can have cruder representations. So I think that'll be a theme that comes up again and again in how people develop, scale up algorithms in quantum computing. I don't know if that's helpful to this discussion, but I think it will go that way.
I'm with you. I'm seeing that motif from quantum chemistry showing up in the QC world. So we usually do something like QMMM, where you do like a hardcore uh, quantum chemistry calculation on 5 atoms of interest, and you have 1,000 like base pair on the side doing pretty much like balls and springs, like just, and then you can refine it. So what I saw in Thomas Mayer's presentation yesterday was also embedding, and you do some work on HPC and then the strongly correlated section of interest or geometry of interest on the QC, and that's the chemistry side of things.
Fault tolerance and then NISC actually could coexist also.
So looking at time, we could move on to the next speaker and get kind of a new thoughts injected and continue the discussion later on, but I don't want to cut off anything here. So any urgent, pressing questions or issues? That is not the case. Smriti, stage is yours.